Hello everybody, I am Mohammed Imran, the president of IMOB, and today we are here with a webinar on fractals. And before moving on to the webinar, I would like to say a few words about the IMOB. And first of all, the IMOB in expanded form can be pronounced as the IMO Busters, and we aim in like cracking Olympiads like RMO and INMO, or you can say Regional Mathematics Olympiad and Indian National Mathematics Olympiad. And we also like have some guest lectures as well, like the one we are having right now. So this is a guest lecture, or you can say a webinar, and we also have some criterias for you to be joining our team. So we usually conduct classes every Sunday from 4 p.m. to 5 p.m. IST, and we just we take a topic on mathematics on the Olympiad area. So we just take a topic and we just discuss that topic, and yeah. So this is what we do, and there is also a selection criteria, as I was saying. So there is one test which is there in our website, and I think that website link is available on the link tree which I had shared in the website. So you can just visit the website, or you would have gotten that link tree from your friends. So you can just go to that link tree and you can see there is a link called IMO Busters website. If you click that, you will be there in our website, and also there is a test on the about section of the website, and there are also various resources which we have provided in the resources tab of the website. So you can visit there, and you can there is a kind of little bit of exploration to do. You can explore there, and there are some other websites where for mathematical learning and all of that. So there is another website wherein which we have linked with, like we have mentioned that website as well. So you can just visit that websites, like around 5 websites we have put in the resources area for mathematical thinking and books and all of that. So you can visit our website, and also you feel free to contact me in my mail. That the mail is also as well provided in the website. You can visit there. Yeah, and now I would like to give it to Nikhil.
Okay, so hello everyone. Good evening, and everyone present here, and to all of those who are following us on the live stream as well. And so I would like to welcome all of you to the mathematical world of fractals, which we'll be delving into today with Ashwath Jain. So before we begin, I'll just want to introduce Ashwath to all of you. So Ashwath is currently a grade 12 student in Pune, Maharashtra, and he is a multifaceted personality, and I know him really well, and you'll realize why I say this in a short while. So a few of his hobbies and talents include he's an avid chess player, he's an artist, and he's also an author. And you'd be surprised to know that he has already authored 2 books, and he's the youngest published author in India. So some of his major achievements also include that he's a KVPY scholar. He has been selected for the prestigious astronomy OCSC camp twice, not once but twice. And also has won several other awards, which include the Inspire Manak Award, which is given by the government of India. And besides that, he has also won numerous competitions, talent search, and whatnot. He has also won Olympiads, Olympiad gold medals at the state and as the national levels. And so now I would like to give it to Ashwath so that he can continue and we can explore this beautiful world of fractals.
Thanks so much, Nikhil, Imran, for that beautiful introduction. Not worthy of it, but all right. So, good evening to one and all present here. We are here to discuss fractals today. So before we move on, does anybody have any guesses what fractals are? Just maybe a one-line definition. You can raise your hand and speak. Just Anybody works. I mean, whatever you know about fractals, even if it's just a very
Graph
basic
of a
idea. Yeah.
complex function. Graph of a complex function.
Graph of a complex function. Okay. Anybody else? Right. So let's delve in. Give me a moment. I'll share my screen. Right. So here we are. And okay, before anything else, is my complete screen visible?
Yeah, it is visible. You can go on.
Cool. So I know this is peculiar and you might not have seen this before, but I will be revealing the title at the end of the lecture, right? So, so that's a suspense that you have to bear, but trust me, it will be worth it. So over the course of this lecture, this webinar, what we'll do is we'll have a small look at the Mandelbrot set. We'll look at what complex exponentiation is. It's not really complex, as in it's not very difficult, but we'll get to it. Then we look at what the limit of a function is. So what a function means, what the limit of a function is. Then we move on to something which all of us have been through, rainbows. All of us know what a rainbow is. And even though it seems kind of mundane to have a rainbow in here, you'll understand why I'm choosing a rainbow at the during the ending part of the webinar. Then we'll finally move to what a fractal is. So we'll use all our concepts from what we've learned in the first 4 or 5 rubrics to get to what a fractal is. Then we'll get to what the dimension of a fractal is. So a sneak peek, spoiler is that it's not usually 1 or 2 or 3 or 4 or any natural number, right? So that's something you can think about. Then we put it all together, right? So we'll have complex exponentiation, limit of a function, rainbows, fractals, and we put it all together to get to coloring fractals. Then I'll show you some images of a fractal, which I think you'll find very interesting. Then conclusion, then I finally reveal the title, and we'll move on to question answers. So this is the Mandelbrot set, right? So some of you may not know about it, some of you may not. However, this is kind of a very popular fractal, in fact, the most popular fractal. So what you can see here is this dark shape with kind of lines coming out of it, green colored lines surrounded by orange. There's a yellow glow around it. You can probably even see some blue and probably even some red. Over here to the left, okay, let me get my laser pointer. So over here to the left, you can see this small thing over here. So that's actually another Mandelbrot set, right? So before we go on, I want to show you a video of the Mandelbrot set. So is the video visible?
Yes, it is visible. You can continue.
Right. So this is a Mandelbrot set, and we're zooming into it. So you can see the shape that we saw back there, and we're still zooming. So you can see these circles and weird shapes coming out of each other. They're black, and they have a distinct boundary. But as we keep moving in, we see that they don't end there. There's a lot of detail that's going on, right? So we're still zooming in, and you see that some really beautiful patterns have evolved here. So there's not only just black, but there's orange and purple, and there's all sorts of different colors. And we're still zooming in, and there just seems to be even more detail, right? So it looks like it's so intricate that we just keep going into it, and doesn't seem to end, right? So it's kind of an infinity. So right now we're zooming in into another part of the fractal, and you can see how intricate this gets, right? Even with just 2 colors, you can see how beautiful these patterns are. So we're still zooming, and we aren't stopping here. So we're still going on. It's purple and orange all the way. And you can, I bet you're mesmerized by the beauty of these fractals. What's even more shocking is that this is purely math. This is nothing else. This is just math. And it's hard to imagine how pure math can actually produce something so intricate, so wonderful, while we have a notion of understanding math as just something like solving for x, right? So I'm going to skip through this video to get to something really interesting. So maybe towards the end. So you can see that this video is just 16 minutes long. There are other videos, say 2 hours, 3 hours long, and the zoom just keeps going on. So what I want to show you here is that a fractal is infinite, right? So you keep zooming in, no matter how hard you zoom, you will always find an infinity in front of you. So you can never reach the end of a fractal by zooming in, right? So you just keep going on and on and on, and it will never end, right? So let's get back to the presentation. So we've seen what a Mandelbrot set is. So this is a fractal, right? So Mandelbrot set over here, this Mandelbrot set is a fractal. Let's move on. So I'll spend maybe just a moment here to discuss something called complex exponentiation. I won't go into the very details of it, but it's good to know about this because this will be something that we'll be using on later in the lecture. So, okay, I'll just pause on the screen for a minute or two, and those of you who are interested can have a look at this. While those of you who are not, it's no big deal, because all we need to know is that this involves something called complex numbers. So what are complex numbers? Complex numbers are just essentially numbers that we cannot plot on the real line. So for example, real numbers are 1, 2, 7, 100, 10,000, million, -3, -5, -1.34, 1.414, 3.414, right? So 3.1415, 9265, so on and so forth. So every number that you can write down like this is a real number. However, complex numbers are something that go beyond these, right? So how do you define the square root of -1? So -1 is technically, you cannot have a real number as the square root of -1. So we define a symbol called I. So you'll see a lot of I's over here in this picture that I've shown you, right? So this I is actually the square root of -1. So those of you who have read through this will have realized that we took a complex number I and we raised it to the power of itself, right? So I raised to I. And we did some weird type of simplification. And in the end, what we got was this number over here, 1 over square root of e raised to pi. So what I want you to realize here is that e is a real number. Pi is also a real number, right? So e has a value of, say, 2.71 something something. And pi is 3.14159265 something something. And the whole is under the square root. And whatever this is, this whole thing over here, this is a real number, right? So this is not imaginary. However, what we started with was completely imaginary. So that was I raised to I. And we have done perfectly logical algebraic manipulations over here to just get to a real number. So that what's beautiful is we take a complex number and we exponentiate it. So raising something to the power is called exponentiation. So that's why this is called complex exponentiation. So there's nothing very difficult in it. The only reason it's called complex is because it is dealing with complex numbers. So this is just something that I wanted you to know because we'll be using a slide part of this in the next slide, but it's okay. Just all you need to know is this thing, x raised to y can be written as e raised to y log of x, but okay. So I'll try not to go into the deep maths over here, but this is just something I wanted to show you that we can write a number like this. So this is the crux of what I'll be showing you today. It's taking a complex number, right? So we represent a complex number by Zn, this thing over here. And we can represent it in two forms, a plus bi or this form. But okay, so all this mathematical manipulation, if you're interested, you can sure have a look at it. But what I essentially want is, I want to show you this equation over here, this Zn plus 1 equal to Zn raised to Zn. So what we did back 2 slides back, we took I and raised it to itself. So I is a complex number. We raised it to itself, complex number, power complex number. And we simplified to get some answer. Same thing we are doing over here. Just that it's not I, it is any general complex number, right? So we are doing that and getting a different complex number, not necessarily always a real number, but a complex number, right? So what we've done here is essentially found a formula. But okay, maths is not really that important in this case because what I'm going to show you will mainly be pictorial. So let's talk about what a function is, what a mathematical function is. So function is essentially nothing. You can consider it like a machine, right? So a machine in which you put in something, like you can see the input written over here. So this is an input. Let's call whatever you're putting in, let's call that x. So you put into the function a thing called x. We don't know what that is, but let's put in something called x. So this machine will operate on x. It will do all sorts of operations that it wishes to do. Maybe cut it in half, or maybe multiply it by 2, or any weird operation which you can imagine of, you can define a function like that. And in the end, it will give out some output. So you put something in, the function does something, whatever the function feels like it does to it, and then it gives out an output. So you give an input and you get an output. So the machine, the function is a machine. So now we know what a function is. What is the limit of a function? So one thing we can do is we can take the output which we got and put it back in. So you put something in, you get an output, and then put that thing back in. So you repeat the process through the machine on the product, and you keep doing this an infinite number of times. So you put something in, get something out, put that back in, get something back out, put that back in, and keep doing this. So when you do this, eventually some functions reach a certain value such that they get constant at a value. That value is what we call the limit of a function, right? Say, for example, I put in 2, and the operation I want the function to do is to half whatever number it gets. So I put in 2, the function halves it and gives me 1. Then I put 1 in, and then the function halves 1 and gives me the output 0.5 or 1/2. Then I put in 0.5, and then it does another half and it gives me 0.25. And I keep doing this unto infinity, and those numbers that I get out keep getting smaller and smaller and smaller and smaller. In the end, I will just get out a number very, 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 very close to 0, right? So you keep halving something and you'll eventually get to 0. So the limit of this function is 0, right? So this is the example to understand what the limit of a function is. So now something very interesting, rainbows. All of us have been acquainted to what rainbows are. We know what rainbows are. So you can see red, orange, yellow, green, blue, indigo, violet, or VIB, GYOR, whichever you prefer it. But this may seem a little unrelated right now, right? So why do we have a rainbow in a fractals lecture? You'll get to know, because this is something that is very common, which you'll see later on. So just wanted to introduce the idea of rainbow, but let's still keep this a question mark about what this exactly signifies over here. So now let's come to what a fractal is finally. So a fractal has 3 properties. I'll stress over these because it's important to know what a fractal is, right? So the first property is that it is self-similar. So what does self-similar mean? Self-similar means that if you zoom in into a fractal, somewhere, not everywhere, but yes, somewhere, you will find the fractal again, the whole fractal again, right? So for a moment, let's just go back to the Mandelbrot set image that I had over here. So I wanted to look at this Mandelbrot set image. This complete thing, whatever you see on the entire page, this is the Mandelbrot set, okay? And as I told you, this small black dot that you see over here is a smaller but still infinite Mandelbrot set. So you have a Mandelbrot set, and that Mandelbrot set contains an infinite number of other Mandelbrot sets, right? So there's one over here. You can see one over here at the top. There's one over here, and there's one over here. And when we went in them, there was something over here, and there are Mandelbrot sets everywhere. And each of those Mandelbrot sets has another infinite number of Mandelbrot sets. And then each of those Mandelbrot sets has yet another infinite number of Mandelbrot sets. So you can imagine how many Mandelbrot sets are there. I mean, okay, let me change it. You cannot imagine how many Mandelbrot sets are there. So there are so many, there are literally infinite Mandelbrot sets over here. So this is what we call self-similar, that when you zoom in, you find the whole fractal once again, right? So it is similar to itself when it is zoomed in. So that's what is called self-similarity. So a fractal, so any picture to be a fractal should be self-similar. Second, it has a simple and recursive definition. So what I mean by definition is that each fractal has a certain function related to it. So for example, the Mandelbrot set, the function is simply x square, right? So you put in a number, a complex number in this case. So you put in a complex number, the function squares the complex number and gives out another complex number. Then you put that complex number in and then squares it and then gives that out. And based on what it gives out with respect to the first input that you gave, this Mandelbrot set is made, right? So what happens is, using a function, you can define a fractal. So by definition, it means that the function should be simple enough. It should not be something like take the 5th root and then raise it to pi, and then take the eth root and then take a log and then half it and then raise it to the power 1/3. And it should not be so complicated. It should be simple, right? Like z square. Just take a number, multiply it by itself, and you're done, right? So it should have a simple and recursive definition. So by recursive, I mean the function should be one that takes the output and gives the output back to the input. So it should go on and on and on, as we saw, up till infinity, right? So that is what is called recursive. Or you can even call it iterative. Iterative as in the same thing. You give something to it and it performs the same operation on the product again and again and again. So iterative or recursive. The third property is that it has a dimension. Although the dimension is very weird, it's something that we are not able to imagine in our everyday lives. So what in our everyday lives, everything is mostly 3D, right? Sometimes maybe if you're working on paper, it may be 2D, or on your screen, it may be 2D, or maybe even 1D. But the dimension of a fractal is a very weird. It's not 1D, 2D, 3D, 4D, any integer D, right? So it's nothing like that. And we'll talk about why that is. So these other properties, these couple of other properties that I listed here, it's infinitely intricate, even at an infinite zoom, right? So as I showed you, the Mandelbrot said, no matter how hard you zoom in, it will still be infinitely intricate. The other property is that they're very beautiful. Of course, you saw the Mandelbrot set, and I'll show you some more pictures later, and you'll appreciate how beautiful they are. Right. So at this point, I'll pause for questions because this has been kind of heavy, I guess. So I'll pause for questions, maybe 5 minutes. If there are any questions, feel free to raise your hand and ask. Absolutely, any questions are welcome. Anything related to this, I'll be happy to answer.
The complex
Yes.
exponential you showed earlier, will it always converge to I raised to I?
No. So what complex exponentiation was that you give a complex number and you raise it to itself, right? So it does not converge to I to the I. I to the I is just 1 by root of e power pi, but not every number converges to that. Okay, just give me a second. Hold on. Yeah. So not every number converges to I to the I, because I to the I itself is a complex exponentiation function, right? So you're given a number and it usually, I'm talking in a general way, it converges to a real number, right? So a lot of numbers converge to 1. That's been something that has been found, right? So what a convergence is that if you, as I said, okay, let me reshare my screen. So as I said, convergence over here is something that is recursive, right? So you keep putting in the thing and then you keep doing it, and then you get a number that does not change a lot. However, we saw that when we put in I to the I, we got a number that was real, right? So I to the I cannot be the limit of this function, because when we put that thing in itself, then the number that we get out is not I to the I or even close to I to the I, right? So that is not the limit of this function. Although we'll see what the limit of complex exponentiation is. We'll get to that in a moment. Yes, any more questions? Feel free.
Hi Ashwath, actually I've got a message from someone. So I've got a question that if you do complex exponentiation infinite times, then do you get a real number?
Yes, in most of the cases. We're coming to that. So complex exponentiation is one of the functions that is recursive, right? So for the example, the Mandelbrot set is a function x square. So you keep squaring the number that you get. Complex exponentiation is another function. You keep raising the number to its own power. There can be other functions, like maybe you take the square root, or maybe you multiply it by half, like you keep halving it, or maybe anything like that. So there can be any function. But yes, if you're talking about the function of complex exponentiation, then it usually converges to a real number. Usually, I'll talk about when it does not, but yes, it usually does converge to a complex number. Oh, sorry, a real number, pardon.
So I think that answers it.
Yeah.
Yes, Shashwat, I think Shashwat has a question. Yes. Yes, Shashwat, you can ask your question.
Shashwat, you're still, yeah, cool. Hello, Shashwat, I can't hear you. Hello?
Hello, Shashwat, are you there? No, I think he put himself on mute.
Probably. Yeah, he's unmuted again.
Are all colorful?
I didn't get you. Could you repeat?
All fractals colorful?
Oh, okay, so the question is, are all fractals colorful, right? So the answer is no. We're coming to an example of, okay, let me just move on. So that will answer your question as well. So we move. So these two fractals that you see over here, these are just black and white fractals. So they're not colorful, right? So not all fractals are colorful. We're also going to talk about how a fractal is made colorful, right? So the two fractals that you see over here, the one on the left is called the Sierpinski gasket or Sierpinski triangle. Either one works. And the one on the right is called a von Koch snowflake, right? So it looks like a snowflake, and it is a fractal, right? So the dimension of a fractal is, so the Sierpinski gasket, the triangle that you see on the left, this has a dimension of 1.585. And this is not something that we see in everyday lives, right? So we don't have something that is 1.5 dimensional or 1.26 dimensional. It's either one dimensional or two dimensional. Like there's nothing in between, right? However, fractals don't obey that. Fractals are something that is beyond what we see in our everyday life, something beyond reality. They're still real, but in a sense, beyond reality. So we saw three properties of fractal, right? They are self-similar, they have a simple and recursive definition, and what was the third one? Can anyone tell me? Okay, anyways, I'll get back. It is a weird dimension, right? So that's what we're talking about. So first condition is that it is self-similar. So you can see that if you take this complete triangle, right, and zoom in, and you get only this triangle, the upper triangle, the upper dark color triangle that you see that this is the same triangle just zoomed in, and it is still infinite, right? So how the Sierpinski gasket is created is just that you keep removing triangles. So you have a completely black triangle, and you remove the central triangle, and then you are left with three smaller black triangles. And then you remove a large central portion from each one of them. So this one, and this one, these three, right? So let me annotate over here. So first you remove this fractal, this triangle. Then you remove this one, and this one. And then you remove, and then you have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 smaller triangles. So then you remove this one, the one that I'm shading over here, this one, and same in all the other 6 triangles, right? So you keep removing it like that. And what you eventually get when you do this an infinite number of times is this whole fractal, which we call a Sierpinski gasket or a Sierpinski triangle. So that done, let's move on to the von Koch snowflake. So the von Koch snowflake is a snowflake, right? It seems like an hexagon. When we zoom in, so let's take one of the 6 parts of this hexagon. And when we zoom in, we see that there is still small bumps and ridges on the hexagon. And when we keep zooming in, so the resolution of this image is not infinite. So that's why we can't see the whole thing here. But if this image did have an infinite resolution, we could have kept zooming in, and we would have got ridges and ridges and ridges and bumps and bumps. So this is a fractal, right? It is self-similar, verified. It has a simple and recursive definition. I'm not going to what the definition of these fractals is, but yeah, you can trust me that they have pretty simple and recursive and iterative definitions. And the third is that it has a dimension, a weird dimension. So you can see 1.26. This does not make any sense, but I'll explain to you why fractals have these kind of fractional dimensions, right? So you can even see the name fractal matches a lot with fraction, right? So one legend is that the name fractal came from these fractional dimensions. So how does the Sierpinski gasket and the one-cut snowflake have these weird dimensions? So let's see. Evidently, the Sierpinski gasket is not one-dimensional, right? If something is one-dimensional, it's just a single line. But the Sierpinski gasket is not a single line. It does not have a dimension 2 either, right? So you notice that as you keep removing triangles, you keep decreasing the area of the triangle, the area of the black part, right? Okay, so let me erase all the markings over here so that we can get a better look here. Right. So as we keep removing triangles, the area that we have left keeps getting smaller and smaller and smaller and smaller. And eventually the area is just 0. But however, if it's a 2D shape, then it should have a finite area, right? So it's neither 1D, neither 2D. And it's certainly not more than 2D, it's not 3D. And it's not 0D, right? Because 0D is just a point. So it's somewhere between 1 and 2D. We proved that. But if it's not 1D, if it's not 2D, then it has to be something fractional, right? So the exact way to calculate why it is only 1.585 and why not 1.4134 something is something beyond the scope of this webinar. But what we can see is that it is certainly between 1 and 2 dimensions, right? The same goes with the one-cut snowflake. The area keeps getting smaller and it's between 1 and 2 dimensions. So it has a dimension of 1.26. For future reference, if you want, there is another fractal, a very simple fractal called the Cantor set. I'll write the name in the chat box if that is helpful. Give me a minute. Okay, Imran, can you do that for me? Just write Cantor set into the chat box.
Yes, yeah, sure. And also, can you write down, can you just tell about the, I don't know the pronunciation of these two fractals. Can you just write it down on the chat?
Okay, sure. Just give me a moment.
Yes.
Yeah, if you want, I can do that.
No, it's okay. I'll be doing that. I found it. Sierpinski gasket or triangle. Yeah. So Sierpinski is actually not an English name, so there's an accent over the E, but I can't type that right now. So Sierpinski gasket or triangle, the one on the left. The one on the right is a one-cut snowflake. One-cut snowflake. And the one I was talking about is a Cantor set. So Cantor set, right? So these are the three fractals, which are, pretty basic to start with. And the Mandelbrot set is like the highest of all fractals, right? So that's the ultimate fractal, you could call it. So let's move on. So we've seen what the dimension of a fractal is. Now let's put it all together. So we started with complex numbers, right? We saw complex exponentiation or complex squaring in case of the Mandelbrot set. Then we saw what the limit of a function is. And now we are going to add colors. And when you add all of this and use the help of computer programming like Python, what you get is a fractal. And it's really amazing that just three very simple things, complex numbers. The name is complex, but they're actually very simple. So complex numbers plus the limit of a function, also very simple, plus colors. Who doesn't know colors? And these three things with a little bit of computer programming give you something so intricate, so beautiful, so infinite that it's kind of awesome how simple math, simple, very elementary concepts of math can give you something that is infinite, right? And it's not just an infinity. It's not a single infinity. It is an infinite number of infinities. So I myself took a lot of time to get my head around this concept, but I'm sure you will get around this. So when you talk about colors, what exactly are we talking about? So while we are doing the fractal maze development, so this is the code. This is one of the codes of a fractal. So there's one fractal I made, right? So complex exponentiation, the function that we were talking about, That fractal, as far as I could search on Google, that did not exist before this. So I essentially created that fractal, and this is a part of the code that I wrote to get that. So you can see it's 154 over here, and it's kind of complicated code. I mean, not a very complicated code, but it'll need some time to go over, and that's not really what we're aiming for this in this webinar. But you can see that we need a little bit of help from the computer programming. So this is how we code, and fractal image development, we saw coloring, right? So someone asked, are all fractals colorful? So here's how we color fractals, right? So this is kind of important because I'll be using this to show how I've colored my fractal. So let me annotate over here. Cool. So based on how quickly the function value escapes to infinity or converges, right? So it's not necessary that every function value will have a limit. So for example, let me just take the function multiply by 2. So you put in any number and keep multiplying it by 2, you will never get a finite number. It will just go off to infinity, right? So the function multiplied by 2 is not something that can have a limit. That is why a function can either escape to infinity, this thing over here, or it can converge, right? So if it does not converge, then it will escape to infinity. So there's one more case, oscillation, but I'm not going into that. Yeah, so based on how quickly the function value escapes to infinity or converges, either of the case, we determine a color, right? So let's put in a number x, and let's see how quickly the function, when we put in x, how quickly the iteration of the function escapes to infinity or converges. And based on how quick that is, we assign a particular color to the number x, right? So number x does not have to be a real number, it has to be a complex number. So now that we've assigned a particular color to the number x, using this color scheme, this color scheme over here, this is called HSV, but you can use other color schemes as well. RGB, for example, red, green, blue, or HSV, hue, saturation, value, but that's just the technicalities which you need not go into right now. So essentially what you just do is you give a color to a number, right? So imagine this, if you had not known anything about functions or limit of a function or anything like that, and someone walked up to you and said, hey, 2 is blue, and that doesn't make sense, right? What do you mean 2 is blue? I mean, 2 is just 2, right? However, with simple concepts like complex numbers and exponentiation, or in general functions, what we've been able to do is we've been able to assign every single number a particular color. And how amazing is that? You use math to assign colors to numbers, right? So that kind of sounds weird at first, but when it comes down in the form of fractals, it's really very hard rendering to see that. It's awesome, right? So let's move on. And now this is what I wanted to show you. Let's get to images, right? So what you see over here is, okay, so you see orange on the left, black on the right, and there's some kind of boundary in between which seems to be yellow, and over here in the center there's some weird business going on. So this is a fractal, and this is the fractal that I've made. So it does not end here, right? So this is like a very zoomed out version of over here, and this is like, that's like the Mandelbrot set. If you zoom out a lot, it will just look like a point, right? So this is what my fractal looks like when it's very, very, very zoomed out. So let's zoom in, right? So this right rectangle over here, let's zoom in and see what that is. Ooh. So when we come in here, we see a lot of different things going on. So first, we can see that in the last image, what we had, like this small bump over here, a bump has actually become something like, it has more bumps inside it, right? So you can see the bumps over here. So we'll analyze what this image shows from left to right, okay? So in the very left, you have these bumps, small bumps and going on. And these bumps actually have rainbows in them. So now you can find the relevance of the fact that I mentioned rainbows over there. So when you look in, everywhere you look, you'll see a rainbow, right? So you look into what the left bumps are. So you'll see red, orange, yellow, green, blue, indigo, violet. And then it starts repeating red, orange, yellow, green, blue, indigo. And so that was about the left part. Then in the center over here, we have something going on. There's a lot of colors over here, and it looks like everything is happening around this point over here. We'll get to that. Then in the center, we have these black colored fingers, sort of projections that are poking out. And in between those black finger projections, we have yellow things, yellow flower petal shaped things that are coming out. And what's interesting is that even these flower petals have rainbows on them, small rainbows, right? So you can see all around this yellow petal, there's a rainbow. Over this yellow petal, there's a there are so many rainbows. Now, what I want to do is, let's zoom into this part, right? So this is where all the action seems to be happening. So we'll also see what's the fingers or finger or whatever this black thing is that is protruding. Let's see what that is. And we'll be looking at what's happening around the center, right? So let's zoom in. So now that we've zoomed in, we have a little clear view of what's going on, right? So over this yellow petal, you can see even the yellow petal has small bumps. So this now has officially classified as a fractal. So let's recall the three things that a fractal needs to be. First, okay, I want someone to recount the definition of fractal to me. Can someone do that? The three conditions.
Yes, Tanmay, I will unmute. Tanmay and Sashwat.
It is self-similar. It has a simple and recursive definition, and it has a weird dimension.
Perfect. So let's see, is this fractal self-similar? You see this fingers poking out of this finger, and then more fingers out of this finger, and then more fingers out of this one, and then it keeps going on and on and on. So it is self-similar, right? Then let's move on to the fact that it has to have simple and recursive definition. So this fractal was created using the z power z definition, and so that's simple enough, right? Take a number and raise it to its own power. That's it. Simple. And it is recursive, that you take a number, raise it to its own power, get out another number, then you take that number and raise it to its own power, then you get out another number, and keep doing this, and what you eventually get will be a real number, most of the cases. Okay. So it is simple. It has a simple and recursive definition. And the third property is that it has a weird dimension. So I'll talk about the dimension of this fractal in a while, but this is now officially classified as a fractal, right? So let's further analyze what this image has to show us. So in this yellow petal, you can see small bumps and rainbows as usual. So no matter how deep no matter how deep we go, rainbows always seem to follow us, right? Rainbows and these fingers, these two things are found everywhere in this fractals for some reason. So let's zoom in, right? So this portion is looking particularly interesting because we are getting to look at the details over here. So we'll crop out what the yellow petals are and let's zoom in. Wow. So what this is that those fingers are not just fingers. Those fingers themselves have small things that small engravings inside them. And what is amazing is that even though we took out the yellow petal, we now have a green petal over here, and then a blue shade over here, and then violet, and then red. And so do you realize what this is? The rainbows are not just like this, red, orange, yellow, green, blue, indigo, but they also form a pattern over here around these fingers. So we had yellow, then green, so red, orange, yellow, green, then blue, then indigo, then violet, and then we're back to red, orange, yellow, green, blue, indigo, violet. It keeps going on and on and on and on and on. And that is the beauty. It's not just these rainbow-shaped rainbows. The rainbows are actually in different forms over here, right? And these fingers, what do these fingers show us? So these fingers have a lot to show us. The first is that out of every projection, out of every bulb, one is the biggest bulb that is emerging. And then on both sides, there are smaller bulbs. And then out of each of those bulbs, you have the same thing repeating, a big bulb and then small bulbs on both sides, and then a big bulb and then small bulbs, and even on the side ones, right? So this essentially is self-similar, right? No matter how hard you zoom in, you will always find these bulbs with an infinite number of bulbs poking out of them, and each of those bulbs having an infinite number of bulbs. So this is just mind-boggling how crazy this can get, right? So we've been here. Let's have one more zoom, right? And then we'll get to what this left part is, what this weird thing going on around this point is. So over here, let's zoom into this white rectangle and see what's happening. So this is a closer zoom in onto one of the fingers that we had, right? So again, there are rainbows everywhere. So I want you to follow the laser pointer, right? My mouse is laser pointer. So there's a rainbow here. There's a rainbow here. There's one here. it keeps going on, and there are an infinite number of rainbows in this small little branch. And then while coming out, there are an infinite number of rainbows. And then in this small region over here, there are an infinite number of fingers, each with an infinite number of fingers, each with an infinite number of rainbows. So the number of infinities, it's so difficult to comprehend. And now I wanted to keep going in over here. And I wanted to see that there are rainbows everywhere, each and every point up to this point, and it just keeps going on and on and on. And no matter how much we zoom, we'll always get a rainbow. Same with the finger. There's this huge black finger over here. And if you can see this, you can keep zooming in and you'll keep getting fingers. The same one like this. And it's just never ending. Keep zooming in, you'll get to infinity. The world will get over, but you can never, ever, ever get to the end of a fractal. And it's so amazing that such a simple equation has produced something so large, right? And yet so small. So let's zoom back out, and we were here. Now let's focus our attention towards this region over here. Something that's weird stuff is happening over here. Ooh. So this is a whole lot of rainbows. So we see that the fingers seem to have disappeared. However, let me warn you, fingers are everywhere. So I want you to look at this small black line that's coming in from the right of the picture, right straight up to the center. And if you look closely, each and every one of this line is actually one of those fingers. And we've zoomed in so much, and yet these fingers are so small. And they keep getting smaller and smaller and smaller and smaller until they reach this point, and that's where they end. But that was about the fingers. What's going on in the whole picture? There's so much of confusion and rainbows and different shapes going on here. So you can see this kind of B shape over here in the very center. So consider yourself lucky if your name starts with B. You're part of a fractal, you could say that. Or if you see this huge circle type thing over here, or the straight line, or something over here, or maybe this full tornado type thing that is seeming to converge at this point. And it's really wonderful, right? So I cannot stress enough on this, how beautiful this is, right? One simple equation leading us to such a deep thing. And I could have zoomed in more, but then that would have taken away the fun. So I'm going to stop here, and I'm going to show you the view of a fractal in a slightly different manner, right? So what you've seen right now has been colored using all the possible colors. However, the only colors that came out were black and the colors of a rainbow. So now let's look at it in a slightly different view. So this is the same fractal zoomed in, and but I've colored it slightly differently. So the purpose of coloring it like this is that now I do not want to see how fast a function diverges, right? So originally our colors were based on how fast a function diverged, right? Or converged. That's what we discussed while we were discussing coloring of a fractal. However, here you see only two colors apart from black, pink and yellow. So this is what I wanted. So this was one of my trial runs. And what I wanted to do with this is to find that numbers did converge, right? So what happens is everything that is in black does not converge. It escapes off to infinity. So black is just black. There's nothing very interesting. So that just escapes to infinity very fast. So nothing very interesting, right? So that's why it's colored black. And the other points outside this, they actually converge. So I wanted to find out what number do they converge to? What is the limit of their function? So for example, this point over here, let's just pick any point, say some point over here in pink. If I put that under complex exponentiation, so I take it, raise it to its own power, take it, raise it to its own power, take it, raise it to its own power, and keep doing this. What number do I get? And right now I want you to appreciate the fact that each of the point in the screen, each of single pixel, even half of a pixel on the screen is actually a number to which we have assigned a color, right? So all of you have seen graph sheets, right? Graph papers. How do we mark numbers on them? So we have an x-axis and a y-axis. Okay, I'll show it from your side. So you have an x-axis and a y-axis, and then you take a number, say number is 3,4. So you go 3 units along the x-axis and 4 units along the y-axis. So that point that you get, that represents the number 3,4. Same is the case with complex numbers. We can represent them on something called the Argand plane, but let's not go into that right now. But essentially, every complex number can be represented like 3, 4 or something, or every complex number has a point on the plane, right? That's the essence of what I wanted to show you here. So every complex number on a plane now has a color attached to it. So the pink color that you see, every number that is in this pink color, every pixel, and that each pixel corresponds to a number. So each of those numbers converges to 1, 0. That is, all of these complex numbers converge to the real number, the number 1, right? So how beautiful is it that you take any complex number that lies in this pink region and put it into a function and tell the function to take input as whatever it throws out, and you keep doing that, and eventually you just get the number 1, the simple number 1. So you might be wondering what these yellow things are for. Yellow is even more interesting. It converges to 0, right? So it's beautiful how just every number on the plane either converges to 1 or to 0 or just escapes to infinity. There's no other possibility, nothing else. Awesome, right? So this is another trial run that I did. This is the same thing, but now what I did was I inverted it. So originally black was for something that diverged off to infinity, and something colorful was for something that actually converged. Here I reversed it. So whatever is in black is actually converging, right? And whatever is in color is actually diverging to infinity. So what looked like simple fingers back then, now we get to know that even in those fingers there is a distinction, right? So initially everything that you see in green and pink and blue and yellow and blue and red and whatever those colors are, so everything that you see here was originally black. However, now that we have focused our attention towards this, we see that this itself has distinctions. So there is a huge pink lobe, and from that you have green lobes coming out, and then from those you have blue, both over here and here and here and all these infinities. And then out of every blue lobe you have yellow lobes coming out. And I just cannot emphasize enough on this. How beautiful is this? I mean, one simple equation and you get this thing. Like, you have all sorts of complications in this, and yet it's so beautiful. So that's it. That's pretty much the end of my talk. So I'll conclude it over here. Okay, I'm just going to read out what's there on the screen. So it's pretty self-explanatory. So you take a complex number, you take a function. So I've just fancily named the function psi of z. You can just consider it any function, whatever you like to call it. You can call it your name. You can call it XYZ. You can call it COVID-19. Whatever the function, you can name it as you like. So iterate the complex number under the function, and you define what a function does. And then you check using Python whether this function converges or diverges. So never bother about this notation over here. If you don't understand it, it's all right. But just check whether the function for a given point converges or diverges. Then, based on how quickly it converges or diverges, assign that number a color, right? So take a color and put it to that number. And voila, your fractal is made. So even though this is a very simple looking 5-step, deceptively simple looking process, it actually took me around, say, 3 months to get this working. So there was a lot of trial and error going on, and I actually had to rewrite my whole code around 2 or 3 times. But in the end, it worked. And you can imagine how happy I was when I actually saw those images. So a big shout out here goes to my sister, who is my cousin, who is currently doing interior designing, and she really helped me with the development of the images. So a big shout out to her, right? So that's it. We have finally reached the end, and now I'm going to reveal the title. Okay, I want you people to suggest titles for this. Does anybody have any suggestions? Like, I want you to name this fractal. What can this fractal be named like, right? So like the Mandelbrot set was named the Mandelbrot set because it was Mr. Mandelbrot who made it, but you cannot name this fractal after me because I don't want that. So I want anyone to suggest a name for this fractal. Feel free. I mean, anything you like. And then I'll tell you what I named the fractal in the end, right? So you can type it in the chat box if you want. If you want to you can unmute and speak. I mean, you can raise your hand, you will get unmuted. So whatever you feel like. So I'll give you, say, 3 minutes to think on this and then resume, right? Cool. So type in anything you have. If you want, type it in the chat box, feel free. Or if you want to raise your hand, feel free. We'll be doing this in exactly 3 minutes from now. Let's go. Okay, we have one. That's interesting. No. Okay. We have another one. It's okay. You can summon multiple entries as well.
There are a few names like Jane, Infinite, and yeah.
It's okay. No issues. I mean, I won't be eventually naming it that, but it's okay. I mean, it's fine if that's it. So you can oh, CE. Oh, okay, nice. That's nice. Okay, I won't speak that out right now. So if you want, if you're sending it to me, either yes, so send it to me so that I can read it, because if you send it to someone else, I won't be able to read it, or just raise your hand, whatever. So if you're sending it to someone else, it's not reaching me. Okay, interesting. So we have around half a minute left. Feel free. Everybody is encouraged to type in the fractal name. Nice. Cool. So we really have some innovative names over here. We have CEO, complex exponentiation. So that's nice. We have infinite to the power of infinite. We have infinite beauty and rainbow fractal. So what I decided to name it was something on the lines of the person who said CEO. I decided to name it ICE. So ICE stands for iterative complex exponentiation. So what we did was iterative, right? So we did that again and again and again and again. So that's why it is iterative. Complex is because it involves complex numbers. Exponentiation is because it involved exponentiation, right? So iterative complex exponentiation, and that's why I like to call this fractal ICE, right? So that's kind of a perky name. So that's what I've named it as ICE, right? So that's the end. And we are on to question and answers. So any questions, anybody from YouTube, if you're watching, you can even you can send questions on YouTube. I think we have people over there to monitor that. And you can ask it in the chat box. Okay, let me open chat to all so that everybody can see the questions. Right. So if you have any questions, feel free to type them to me or to everyone, whatever feels right, or you can even raise your hand. Either one works. So any questions relating to any part of the talk, anything that you might not have found clear, anything that you wanted to inquire more, anything in general about fractals, not necessarily about ICE, or maybe what the Mandelbrot said, or anything that you wish to ask. Yes,
Yes,
Tanmay.
Tanmay. I think Tanmay has something.
Yeah.
Yes.
Oh, you're unmuted.
What is the dimension of ice?
Ah, right. Thanks for reminding. I forgot to mention that. So I calculated the dimension, and okay, I wanted to guess. Will it be 1 point something something, or 2 point something something, or 3 point something something, or maybe even 0 point something something? So I'll show you the image of ice once again, and I want you to guess the dimension. Is it between 1 and 2, between 2 and 3, or between 3 and 4, maybe, or between 0 and 1? So this is what ice. So what everybody, what do you feel the dimension is? Type it in the chat box. I want to watch. Between 1 and 2, between 2 and 3, between 0 and 1, 3 and 4. 1 point something, between 2 and 3, okay. between 1 and 2. Nice. Just 3 answers. Come on, everybody, you can type. So I'll wait for 2 more answers, right? So type quick. Let's see what the majority says. Between 1 and 2, okay? One more, come on. Okay, so we have between 1 and 2. So the majority is correct. It is between 1 and 2, and it actually came out to be 1.42, right? So, okay, that was not okay. So we saw the Sierpinski gasket and the one-coat snowflake. So the dimension of ice is less than the dimension of the Sierpinski gasket. So Sierpinski is 1.58 and ice is 1.42, while that is greater than 1.26. So ice, in a sense, lies somewhere between both of these, right? So it cannot lie between 2 and 3, because to lie between 2 and 3, it would have to be somewhere between 2-dimensional and 3-dimensional. So of course it is somewhere near 2-dimensional, but no part of it is coming out of the screen, right? So it is not 3-dimensional. So it cannot be between 2 and 3. So it has to be between 1 and 2, right? Cool. Nice question. Thanks for reminding once again. Any other questions?
Yeah, so I've got a question from, okay, I'll not take the name, but we have got a question that what is the dimension of the Mandelbrot set?
Ah, okay, nice. So Mandelbrot set is actually, the dimension of the Mandelbrot set is actually not particularly defined. How do I explain this? Because Mandelbrot set is something that actually encompasses a lot of things. So I don't know. So okay, what I can tell you is there are different types of dimension measuring techniques, right? So one is called the Bouligon dimension. One is the Minkowski dimension. There's another called the Hoffman, or I forget the name, something like that dimension. So it depends on what the technique of the dimension is. So maybe the Minkowski dimension comes out to be, say, something like 1.42, and the Bouligon dimension comes out to be, say, 1.47. They're always close, but they are not exactly the same. So the problem with the Mandelbrot set is that when we try to calculate it, it's quite different with different techniques. So there is still no very clear agreement about that. But in general, people tend to assume it as completely 2-dimensional figure, right? So that's kind of weird because fractals usually don't have integer dimensions. But yeah, so even Mandelbrot set has different dimensions in different ways, but yeah, usually you can consider it to be 2 in a very vague sense. So do not confuse this with do not assume this to be okay. So do not say, look at this set like I am saying that dimension of the Mandelbrot set is 2. It is not 2, and yet it is 2. Like, so it's a gray area. We can't put up hand down on it. Nice question. Hausdorff dimension of Mandelbrot set. Yes, that's the name. Yeah. So that is approximately 2.
Okay, so do we have any more questions? Everyone feel free to ask any questions if you have.
Actually, I do have a question.
Yeah, go on.
So, is there any way to differentiate like between, like, is there any way to find which dimension of which fractal is greater? Like, you don't directly calculate the fractal's dimension. Like, so you see here you have the Sierpinski gasket, and there you have, the one-cot snowflake. So, like, without even like finding the values, finding the dimensional value of both of the fractals, is there any way to like find or is it possible to even like just know which dimension is greater?
So
Between
one
Sierpinski
obvious way could be, although this won't apply for fractals that have, whose dimensions are very close by together, but let's take the example of these 2 fractals that are on the screen. So you can see that the Sierpinski gasket is much more filled than one-cot snowflake. And a one-cut snowflake boundary actually resembles a line more than Sierpinski gasket, right? So the one-cut snowflake will have a dimension closer to 1 than to 2. However, the Sierpinski gasket is closer to 2 dimensions than it is to 1 dimension. So that's why this is more than this. So this is a very vague method. I mean, it's not always easy to compare two fractals just by looking at them. So usually mathematical analysis is required. But yes, in some simple cases like this, we can differentiate between them.
Okay, so
Yeah,
we have another question, and the question is that is there any fractal which has higher dimensions than our 3 dimensions? So we have fractals with dimensions that are more than 3, and if so, then how do they look like? So how will we imagine them to be, or like how do we see them in this world?
Okay, so let's look at it like this. So this thing over here, this is 1.585 dimensional. We have successfully represented it on a 2D plane, right? We've been able to represent it on a 2D plane. Similarly, this 1.26 dimension fractal, we have been able to put it onto a 2D paper or 2D screen. Same way, if there is a fractal that is 3 point something something dimensional, then in certain cases, we might be able to portray it in 3 dimensions, right? So a fractal is essentially just a mathematical concept, right? So there's no actual, like you cannot hold a fractal in your hands because that's not something that is actually tangible. You can hold a printout of a fractal in your hand, but then what you'll be holding in your hand will not be a fractal. It'll just be a piece of paper with some print on it, ink on it, right? That won't be actually a fractal. So even what you're seeing on the screen, these aren't very true fractals because they have been put on a screen. In essence, if you wanted to show a fractal, we could not show a fractal because you can't put it on the screen, you can't put it on paper, you essentially can't show a fractal, right? So these are just mathematical concepts which look very beautiful, to be honest, which we have been able to represent here. Same thing, if we have a 3 point something dimensional, then we can represent it in 3 dimensions, right? However, it'll look like an ordinary 3-dimensional thing to us. Just like at first glance, this looks like an ordinary 2-dimensional thing, right? So same way that will look like a 3-dimensional thing, but it may have a dimension between 3 and 4. So active research is actually still ongoing on these topics.
Yeah, just building on top of that, from what I know, we have had a 3-dimensional fractal which is called the Mandelbrot.
Mandelbrot, true.
Constructed really recently, and you can just look it up on Google. Just look at how it looks like, and it really it can be imagined. I mean, you can imagine it in 3 dimensions, like what you said.
So the Mandelbulb is the 3D counterpart of the Mandelbrot set, right? So that's why the name Mandelbulb. And there's also something called the Buddha-brot. So if you're interested, you can actually go to Google and check out something called the Buddha-brot, Mandelbrot. You can just search for fractals and you'll see a lot of fractals over there, right? So there are flowers, and then there's random integer walk fractals and accumulation fractals and all sorts of different things over there. So you can go to the internet and just Google up fractal and different kinds of fractal. And although mostly you'll see the Mandelbrot set because that's the most famous. But yeah, there's so many different fractals out there.
Okay, so we have another question that is, are there any applications of fractals, or is there any prediction of their application in future? Like, is it supposed to be used soon or?
Okay, so let me tell you this. Nearly everything in nature is a fractal. It's not a perfect mathematical fractal, but over a range of scales, it's a fractal, right? So for example, let's consider a mountain, right? So consider a mountain on the whole, right? So you have something that goes like this. And then you zoom in onto the mountain, and then you find a rock that's something like this. In a sense, not perfectly exactly the shape of the mountain, but it's something like this. And then you zoom in on the rock, and then you see small spikes on the rock or something, roughness on the rock that with each ridge looking like a very small mountain. And then you zoom in, and then in each section you find something that looks like a mountain, right? Not maybe every time, but yes, on the whole, a mountain can be considered to be a fractal, right? So maybe you go up into the International Space Station, say for example, and you're orbiting the Earth, and you look down at the Himalayas, and you see that there are a lot of mountains in the Himalayas out there, right? And then when you come back to Earth, you go on one particular mountain, and then you see that mountain. And then on that mountain, you see a lot of different small pebbles. And then if you keep going in over a certain range of scales, mountains can behave like fractals. Another example, let's take a river. So you have a flowing river, right? And then it splits into two. And then each of those branches may split into two or three. And then each of those may split. So you have one single stream. And then when you zoom in, you have stream splitting, right? So in a sense, rivers are fractals. Of course, they're not perfect fractals because you cannot have rivers going on up till an infinite zoom. They'll end at some point. But yes, over a wide range of scales, they are fractals. So a lot of different things in nature can be found as fractals. You see lightning bolts, clouds, even leaves or mountains, or as I said, rivers, or there are coastlines. A very famous example is coastlines. So if you are interested, Google up. There's an experiment called measuring the coastline of Britain, and that involves fractals, right? So just Google up fractal Britain coastline, and if you read through, you'll find something very interesting.
Okay, so I've just posted out a link in the chat, and it's a link of a YouTube video which just takes us on a tour of a three-dimensional fractal, just like we had this zooming of the Mandelbrot fractal when we started the lecture, and it's just beautiful. It's still remains one of the most beautiful things. Okay, so do we have any more questions?
Is someone monitoring YouTube? Do we have any questions from YouTube?
No, up till now we don't seem to have any questions from YouTube.
No issues.
Okay, so I guess we don't have any the questions right now,
Okay.
And so we can stop for now. And if you want to say anything, Ashwath.
So essentially, we've been through a lot in this webinar. It's been around an hour, and we've seen what iterative complex exponentiation is. So that's the end. Thank you all for being here. You can reach out to me anytime at my email ID. It's there on the screen. It's just simply jan.ashwath@gmail.com. In case of suggestions, feedback, queries, in fact, even if you have something, if you get a doubt after this, if you're thinking about this, drop me a mail. I'll get back, right? So thank you everyone for being here. Thank you, Imran. Thank you, Nikhil. Thank you, IMO Busters, for giving me this platform to present this. Thank you.
Yeah, sure. So just as we were going through all the presentations today, we really we got involved with so many amount of infinities with the help of these fractals, which are so beautiful structures, which are constructed simply through mathematics. And this is one way in which we can look at mathematical beauty in its and it's in its own sense, and it cannot be portrayed in any other way. So I would just like to quote, fractals are a way of seeing infinity. This is what was said by Benoit Mandelbrot, and this really seems true as of now when we have had a look at this brilliant presentation by Ashwath. So I would like to thank all of you for being a really nice audience to us and attending this session wholeheartedly. And we are also grateful to Ashwath, who has taken out his precious time for us. And as usual, he has been absolutely wonderful. And so thanks a lot, everyone, and stay safe, and goodbye for now. And hopefully we'll be meeting really soon.
Right. Thank you.
Thank you very much, Nikhil. Thank you very much, Ashwath, for, the session was really wonderful. I think all of you would have enjoyed it as much as we did. And yes, so yeah, so I hope all of you enjoyed it. And yeah.